12th। आज हम लोग यहाँ पे केमिस्ट्री का फर्स्ट पार्ट का चैप्टर फर्स्ट पढ़ने वाले हैं, सोल्यूशन। We rarely come across pure substance. Most of these are mixture containing two or more pure substance. Their utility or importance in life depends on their composition. For example, the properties of brass, mixture of copper and zinc, are quite different from those of German silver. Mixture of copper, zinc, and nickel. Bronze is mixture of copper and tin. 1 part per million, that is ppm of fluoride ions in water prevent tooth decay, while 1.5 ppm cause the tooth to become malted and high concentration of fluoride ions can be poisoned. For example, sodium fluoride is used in rat poison. Intravenous injection are always dissolved in water containing salt at particular ionic concentration that match with blood plasma concentration and so on. In this unit, we will consider mostly liquid solution and their formation. This will be followed by studying the properties of solution like vapor, pressure, and colligative properties. We will begin with the type of the solution and then various alternative which concentration of a solute can be expressed in liquid solution. Solutions are homogeneous mixture of two or more than two components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in large quantities is known as solvent. Solvent determine the physical state in which solution exists. One or more component present in solution other than solvent are called solute. In this unit, we shall consider only binary solution, that is expressing concentration of solution. Composition of solution can be described by expressing its concentration. The latter can be expressed qualitatively or quantitatively. For example, qualitatively we can say that solution is dilute, that is relative very small quantity of solute, or it's concentrated, that is relatively very large quantity of solute. But in real life, these kind of description can be added to a lot of confusion and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of solution quantitatively. Mass percentage, that is W by W. The mass percentage of a component in solution is defined as mass percentage of the component. Mass of the component in a solution that upon total mass of the solution into 100. For example, if a solution is described by 10% of glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, resulting in 100 gram of solution. Concentration described by mass percentage is commonly used in industrial chemical appliances. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. Volume percentage. The volume percentage is defined as volume percentage of component. Volume of the component by total volume of solution into 100. For example, 10% of ethyl alcohol in solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of the solution is 100 ml. Solution containing liquids are commonly expressed in this unit. For example, a 35% of volume by volume solution of ethyl glycol and antifreezing is used in car for cooling an engine. At this concentration, the antifreezing low the freezing point of water at 255.4 K, that is minus 17.6 degrees Celsius. Mass by volume percentage. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of the solute dissolved in 100 ml of solution. Parts per million. When a solute is present in trace quantity, it is convenient to express concentration in parts per million and is defined as parts per million. Number of parts of the component, total number of parts of all components of solution into 10 to the power 6. As in the case of percentage, concentration in parts per million can be expressed as a mass by mass to volume by volume and mass to volume. A liter of seawater, which weight 1030 grams, contain about 6 into 10 to the power minus 3 grams of dissolved oxygen. Such a small concentration is also expressed as 5.8 per 10 to the power 6 gram, that is 5.8 ppm of seawater. The concentration of pollutant in water or atmosphere is often expressed in terms of micron, milliliter, or ppm. Mole fraction. Commonly used symbol for mole fraction is X, and subscript used on the right hand side of X denote the component. It is defined as mole fraction of a component, number of moles of the component upon total number of moles of all components. For example, in a binary mixture, if a number of moles of A and B are Na and Nb representatively, the mole fraction of A will be Xa is equals to Na upon total number of moles, that is Na plus Nb. For a solution containing I number of component, we have Xi is equals to Ni and 1, 2, 3 up to the Nn, Ni that is Ni sigma n Ni. It can be shown that in a given solution, sum of all the mole fraction is unity. That is, it can be shown that in a given solution of sum of all the mole fraction is unity. That is, x1 plus x2 is up to xi is equals to 1. Mole fraction unit is very useful in relating some physical properties of solution, say vapor pressure, with the concentration of the solution, and quite useful in describing the calculation involving gas mixture. Molarity is defined as the number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Molarity is defined as the moles of solute upon volume of solution in liter. For example, 0.25 mole per liter or 0.25 mole solution of NaOH means that 0.25 mole of NaOH has been dissolved in 1 liter or 1 cubic decimeter. Molality, that is defined by small m, is defined as the number of the moles of solution, number of moles of solute per kilograms or solvent, and is expressed as molality small m is moles of solute upon mass of solvent in kg. For example, 1 mole per kg or 1 small m solution of KCl represent 1 mole of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solution has its own merit and demerit. Mass percentage, ppm, mole fraction, and molality are independent of temperature, whereas molarity is a function of temperature. This is because volume depends on the temperature and the mass does not. Solubility. Solubility of a substance as its maximum amount of that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of the solute and solvent as well as the temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. Quality of solid in liquid. Every solid does not dissolve in a given liquid, while sodium chloride and sugar dissolve readily in water. Naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that a polar solute dissolves in polar solvent and non-polar solute in non-polar solvent. In general, a solute dissolves in a solvent if the intermolecular interaction are similar into, or we may say like dissolve in like. When a solid solute is added to solvent, some solute dissolves as its concentration increases in solution, and this process is known as dissolution. Some solute particles in solid collide with solid solute particles and get separated out of solution. This process is known as crystallization. It is reached when two processes occur at the same rate. Under such condition, number of solute particles going into solution will be equal to the solute particles separating out, and a state of dynamic equation is reached. Solute plus solvent is equals to solution. At this stage, the concentration of solution will remain constant under the given condition, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvent. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called saturated solution. An unsaturated solution is one in which more solute can be dissolved at a same temperature. Is in dynamic equilibrium with undissolved solute is the saturated solution and contain the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is called its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substance. In addition to these variables, two other parameters, that is temperature and pressure, also control this phenomena. Effect of temperature. Effect of temperature. The solubility of solid in a liquid is significantly affected by temperature change. Consider the equilibrium represented by equation. This being dynamic equation must be Le Chatelier principle. In general, if in a near saturated solution, the dissolution process is endothermic. That is, enthalpy of sol is greater than zero. The solubility should increase with rise in temperature, and if it is exothermic, that is, enthalpy of solution is less than zero, the solubility should decrease. These trends are also observed experimentally. Effect of pressure. Pressure do not have any significant effect on solubility of solid in liquid. It is so because solid and liquids are highly incompressible and practically remain unaffected by change in pressure. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen in which sustains all aquatic life. On the other hand, hydrogen chloride, that is hydrogen chloride gas, that is HCl, is highly soluble in water. Solubility of gas in liquid is greatly affected by pressure and temperature. The solubility of gas increase with increase of pressure. For solution of gas in a solvent, consider a system as shown in figure 1.1a. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume the system to be in a dynamic state of dynamic equilibrium, that is, under these conditions, rate of gaseous particle entering and leaving the solution phase in the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. This will increase the number of gaseous particles per unit volume over the solution, and also the rate at which the gaseous particles are striking the surface of solutions to enter it. So the solubility of the gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of gases above the solution, and thus its solubility increase. Henry was the first to give a quantitative relation between pressure and solubility of gas in a solvent, which is known as Henry's law. The law states that at constant temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in liquid solution is a function of partial pressure of the gas. If we use the mole fraction of gas in the solution as a measure of its solubility, then it can be said that the mole fraction of a gas in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry law states that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of gas small x in the solution, as expressed in P is equals to Kh into x, where Kh is the Henry's law constant. If we draw a graph between partial pressure of the gas versus mole fraction of the gas in solution, then we should get a plot of typical type as shown in figure 1.2. Different gases have different Kh value at the same temperature. This suggested that Kh is a function of the nature of the gas. It is obviously from equation 1.11 that a higher value of Kh at a given pressure, the lower is the solubility of gas in the liquid. It can be shown in table 1.2 of then Kh value for both N2 and O2 increase with increase of temperature, indicating that the solubility of gases increase with decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold water rather than in warm waters. Henry law finds several applications in industries and explains some biological phenomena. Notable among these are to increase the solubility of O2 in soft drinks and soda water. The bottle is sealed under high pressure. The scuba divers most cope with high concentration of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gas in blood. When the diver comes towards the surface, the pressure gradually decreases, and this releases the dissolved gas and lead to the formation of bubbles of nitrogen in the blood. This blocks capillaries and create a medical condition known as bends, which are painful and dangerous to life. To avoid bends as well as the toxic effect of high concentration of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium, that is 11.7% of helium and 56.2% of nitrogen and 32.1% of oxygen. At high altitude, the partial pressure of oxygen is less than at the ground level. 2. Low concentration of oxygen in the blood and tissue of people living at high altitude or climber. Low blood oxygen cause climber to become weak and unable to think clearly. Symptom of condition known as anoxia. Effect of temperature. Solubility of gas in liquid decreases with rise in temperature. When dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learned in the last section that dissolution process involves dynamic equilibrium and thus must follow Le-Chatelier principle. As dissolution is an exothermic process, the solubility should decrease with increase in temperature. Vapor pressure of liquid solution. Liquid solution are formed and solvent is a liquid. The solute can a gas, a liquid, or a solid. Solution of gas in liquid have already discussed in section 1.3.2. In this section, we will discuss the solution of liquid and solid in a liquid. Such solution may contain one or more volatile components. Generally, the liquid component is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solution, that is, the solution containing two components, namely solution of ion in liquid and second is solid in liquid. Vapor pressure of liquid in liquid solution. Let us consider a binary solution of two volatile liquid and denote the two components as first and second. We Taken in a closed vessel, both the component would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be total P total and P1 and P2 be the partial vapor pressure of the two components 1 and 2 respectively. These partial pressure are related to the mole fraction of X1 and X2 of the two component 1 and 2 respectively. The French chemist Francois Marty Raoult 1886 gave the quantitative relationship between them. The relationship is known as the Raoult's law, which stated that for a solution of volatile liquids, pressure of each component of the solution is directly proportional to its mole fraction present in solution. Thus, for component 1, P1 is directly proportional to H1, and the equation is P1 is equal to P1 naught into X1. P1 naught is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, P2 is equal to P2 naught into X2, where P2 naught 2 represents the vapor pressure of the pure component 2. According to Dagger's law of partial pressure, the total pressure P total over the solution phase in the container will be the sum of the partial pressure of the component of the solution and is given as P total is equal to P1 plus P2. Substituting the value of P1 and P2, we get P total is equal to X1 into P1 naught plus X2 into P2 naught is equal to 1 minus X2 into P1 naught plus X2 into P2 naught. P1 naught is equal to P2 naught minus P1 naught into X2. Following conclusion can be drawn from equation 1.16. Total vapor pressure over the solution can be related to the mole fraction of any one component. Total vapor pressure over the solution varies linearly with the mole fraction of component 2. Depending on the vapor pressure of the pure component 1 and 2, total vapor pressure over the solution decrease or increase with increase of the mole fraction of component 1. A plot of P1 and P2 versus the mole fraction of X1 and X2 for a solution gives a linear plot as shown in figure 1.3. These lines, first and second, passes through the point from which X1 and X2 are equal to unity. Similarly, the plot line 3 of P total versus X2 is also linear. The minimum value of P total is P1 naught and the maximum value of P2, assuming that the component 1 is less volatile than the component 2. That is, P1 naught is less than P2 naught. The composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. If Y1 and Y2 are the mole fraction of the component 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressure, P1 is equal to Y1 into P total and P2 is equal to Y2 into P total. In general, Pi is equal to Yi into P total. Raoult's law as a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by P1 X1 into P1 naught. In the solution of a gas in a liquid, one of the component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which stated that P is equal to Kh into X. If we compare the equation for Raoult's law and Henry's law, it can be seen that the partial pressure of the volatile component or gas is directly proportional to its mole fraction in solutions. Only the proportionality constant Kh differs from the P1 naught. Thus, Raoult's law becomes a special case of Henry's law in which Kh becomes equals to P1 naught. Vapor pressure of a solution of solid in liquid. Another important class of solution consists of solid dissolved in liquid, for example, sodium chloride, glucose, urea, and cane sugar in water and iodine in solution, sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvents. For example, vapor pressure liquid at a given temperature vaporizes and under equilibrium condition, the pressure exerted by the vapor pressure of liquid over the liquid phase is called vapor phase. Figure 1.4a. In a pure liquid, the entire surface is occupied by the molecule of liquid. If a non-volatile solute is added to a vapor pressure of a solution is solely from the solvent alone. This vapor pressure of a solution at a given temperature is found to be lower than the vapor pressure of pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules, thereby the fraction of a surface covered by the solvent molecule gets reduced. Consequently, the number of solvent molecules escaping from the surface is corresponding reduction. Thus, the vapor pressure is also reduced. The decrease in vapor pressure of a solvent depends on the quantity of non-volatile solute present in the solution. Irrespective of its nature, for example, decrease in the vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. Raoult's law in its general form can be stated as For any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be pressure of solvent. X1 be its mole fraction, P1 not be its vapor pressure in the pure state, then according to Raoult's law, P1 is directly proportional to X1. Then P1 is equals to X1 into P1 naught. The proportionality constant is equals to the vapor pressure of pure solvent, P1 naught applied between the vapor pressure and the mole fraction of solvent in linear. Ideal and non-ideal solution. Liquid-liquid solution can be classified into ideal and non-ideal solution on the basis of Raoult's law. The solutions which obey Raoult's law are over the entire range of concentration are known as ideal solution. The ideal solution have two important properties. The enthalpy of mixing of pure component to form solution is zero and the volume of its mixing is also zero. That is enthalpy of it is equals to maximum is zero and V maximum is also zero. It means that no heat is observed or evolved when the components are mixed. Also, the volume of solution would be equals to the sum of volumes of the two components. At molecular level, ideal behavior of be expressed by considering the two component A and B. In pure component, the intermolecular force of attraction interaction will be type of A and B and B. Whereas in binary solution, in addition to these two interactions, AB type of interaction will also present. If the interaction attractive, if the intermolecular attractive force between A and B are nearly equal to those of AB, this leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. fall in this category. Non-ideal solution. When a solution does not obey Raoult's law over the entire range of concentrations, then it is called non-ideal solution. The vapor pressure of such solution is either higher or lower than the predicted by Raoult's law. It's higher, the solution exhibits positive deviation, and in its lower, it exhibits negative deviation from Raoult's law. The plot of vapor pressure as a function of mole fraction for such solution are shown in figure 1.6. The cause for these deviations lie in the nature of interaction at the molecular level. In case of positive deviation from Raoult's law, A and B interaction are weaker than those of A and B. That is, in this case, the intermolecular attractive force between the solute and solvent molecule are weaker than those between the solute-solute molecule and solvent-solvent molecule. This means that in such solution, a molecule of A or B will find it too easier to escape than in pure state. This will increase the vapor, result in positive deviation. Mixture of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecule and break some of the hydrogen bond between them. Due to weakening of interactions, the solution show positive deviation from Raoult's law. Figure 1.6a. In a solution formed by adding carbon disulfide to acetone, the dipolar interaction between solute-solvent molecules are weaker than the representative interaction among the solute-solute and solvent-solvent molecules. This solution will also show positive deviation. In case of negative deviation from Raoult's law, the intermolecular attraction between A and B are weaker than those between A and B and leads to decrease in vapor pressure resulting in negative deviation. An example of this type is a mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atom of aniline is stronger than representative intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms are solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule as shown. Decrease the escaping tendency of molecule for each component and consequently the vapor pressure decrease resulting in negative deviation from Raoult's law. Some liquids on mixing form isotropes which are binary mixture having the same composition in liquid and vapor phase and boil at the constant temperature. In such cases, it is not possible to separate the component by fractional distillation. There are two types of azerotropic called minimum boiling azerotrops and maximum boiling azerotrops. The solution will show a large positive deviation from Raoult's law for minimum boiling azerotrope at a specific composition. For example, ethanol water mixture obtained by fermentation of sugar on fraction distillation give a solution containing approximately 95% by volume of ethanol. Once this composition known as azeotropic composition has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solution that show large negative deviation from Raoult's law form maximum boiling azeotropic at specific composition. Nitric acid in water is an example of this class of azeotrope. This azeotrope has the maximum composition, that is 68% of nitric acid and 32% water by mass, with a boiling point of 393.5 Kelvin. Colligative properties and determination of molecular mass. We have learned in section 1.4.3 that vapor pressure of solution decrease when non-volatile solute is added to a volatile solvent. There are many properties of solution which are connected with these decrease of vapor pressure. These are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, and osmotic pressure of the solution. All these properties depend on the number of the solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative property. Colligative from Latin co means together, ligate means to bind. In the following section, we will discuss these properties one by one. Relative lowering of vapor pressure. We have learned in section 1.4.6 the vapor pressure of a solvent in solution is less than that of pure solvent. Raoult established that lowering of vapor pressure depends only on the concentration of the solute particles and it's independent of their identity. The equation 1.20 given in section 1.4.3 establishes a relationship between vapor pressure of the solution and mole fraction and vapor pressure of the solvent, that is P1 is equal to X1 into P1 naught. The reduction in the vapor pressure of solvent P1 naught is given as P1 naught minus P1 is equal to P1 naught minus P1 into X1. P1 naught is equal to 1 minus X1. Knowing that X2 is equal to 1 minus X1, equation 1.23 reduced to delta P1 is equal to X2 into P1 naught. In a solution containing the several non-volatile solutes, the lowering of vapor pressure depends on the sum of the mole fraction of different solute. Equation 1.24 can be written as P1 is equal to P1 naught is equal to P1 naught minus P1 upon P1 naught is equal to X2. On the left hand side of equation, as mentioned earlier in relative lowering of vapor pressure N is equals to the mole fraction of the solute. The above equation can be written as P1 naught minus P1 upon P1 naught is equals to N2 upon N1 plus N2. Since X2 is equal to N2 upon N1 plus N2. Here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. For dilute solution, N2 is much lesser than N1. Hence, neglecting N2 in the denominator, we have P1 naught minus P1 upon P1 naught is equal to N2 minus N2 by N1. Or P1 naught minus P1 upon P1 is equal to W2 into M1 upon M2 into W1. Here, W1 and W2 are the masses and the M1 and M2 are the molar masses of the solvent and solute respectively. For this equation 1.21 to 8, knowing all the other quantities, the molar mass of solute M2 can be calculated. Elevation of boiling point. The vapor pressure of a liquid increases with increase of temperature. It boils at the temperature at which vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin, that is 100 degrees Celsius. Because of this temperature, the vapor pressure of water is 1.013 bar, that is 1 atmosphere. We have also learned in the last section that vapor pressure of solvent decreases in the presence of non-volatile solute. Figure 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent water. Thus, the boiling point of a solution is always higher than that of boiling point of pure solvent in which the solution is prepared, as shown in figure 1.7. Similar to lowering of vapor pressure, the elevation of boiling point also depends on the number of the solute molecules rather than their nature. A solution of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let Tb not be the boiling point of pure solvent and Tb be the boiling point of solution. The increase in the boiling point del Tb is equal to Tb minus Tb naught is known as elevation of boiling point. Experiments have shown that for dilute solution, The elevation of boiling point, that is del TB, is directly proportional to the mole concentration of the solute in a solution. Thus, del TB directly proportional to small m, or del TB is equal to Kb into m. Hence, m small m is the molality in the number of moles of solute dissolved in 1 kg of solvent. As a constant proportionality, Kb is the boiling point elevation constant or molar elevation constant, ebullioscopic constant. The unit of Kb is K kg per mole. Value of Kb for some common solvent are given table 1.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution at the expression. M is equal to W2 upon M2 upon W1 upon 1000 is equal to 1000 into W2 upon M2 into W1. Substituting the value of molality in equation 1.30, we get del TB is equal to Kb into 1000 into W2 upon M2 into M1. M2 is equal to 1000 into W2 into Kb upon del TB into W1. Thus, in order to determine M2 molar mass of solute, known mass of solute is in an unknown mass of the solvent is taken, and TB is determined experimentally for a known solvent whose Kb value is known. Question of freezing point. The lowering of vapor pressure of solution causes a lowering of the freezing point compared to that of pure solvent. We know that at the freezing point of a substance, the solid phase is in dynamic equilibrium with its liquid phase. Thus, the freezing point of substance may be determined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent as the clear form. Figure 1.8 according to Raoult's law. When a non-volatile solid is added to solvent, its vapor pressure decreases, and now it would become equal to that of solid solvent at lower temperature. Thus, the freezing point of the solvent decrease. Let Tf not be the freezing point of pure solvent and Tf be its freezing point. When non-volatile solute is dissolved in it, the decrease in freezing point. Tf is equal to Tf naught minus Tf is known as depression in freezing point. Similar to elevation of boiling point, depression of freezing point, that is del TF, is dilute solution. Ideal solution is directly proportional to molality, small m of the solution. Thus, Tf is directly proportional to m, or del TF is equal to Kf into m. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant, or molal depression constant, or cryoscopic constant. The unit of Kf is K per mole. Value of Kf for some common solvent are listed in table 1.3. If W2 grams of solute has molar mass as M2 present in W1 gram of solvent, reduce the depression in M freezing point Tf of the solvent, then molality of the solute is given by the equation 1.3. M is equals to W2 upon M2 by W1 by 1000. Substituting this value of molality in equation, def is equals to Kf into W2 into 1000, M2 into W1. M2 is equal to Kf into W2 into 1000 upon del Tf into W1. Thus, determining the molar mass of the solute, we should know the quantities W1, W2, Tf along with the molar freezing point of depression constant. The value of Kf and Kb, which depend upon the nature of the solvent, can be asserted from the following relation. Ki is equals to R into M1 into Rf square upon 1000 into del fusion H. Kb is equals to R into M1 into Tb square, whereas upon 1000 into enthalpy of vapor pressure. Here, the symbol R and M1 stand for gas constant and molar mass of solvent, respectively, and Tf and Tb denote the freezing point and boiling point of the pure solvent, respectively, in Kelvin. Further, enthalpy of vaporization represents enthalpy for the fusion and vaporization of the solvent, respectively. Osmotic pressure. There are many phenomena in which we observe in nature at home. For example, raw mango shrivels when pickled in brine, salt water. Wilted flower revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. We will look into this process. We find one thing common in all, that is, all these substances are bounded by membrane. These membrane can be animal or vegetable origin, and these occur naturally, such as pig bladder or parchment, or can be synthetic, such as cellophane. These membrane appears to be continuous sheet or films, yet they contain a network of submicroscopic holes or pores, small solvents molecule Like water can pass through these holes but the passage of bigger molecule like solute is hindrance. Membrane having this kind of properties are known as semi-permeable membrane or SPM. Assume that only solvent molecule can pass through these semi-permeable membrane. If these membrane is placed between the solvent and solution and shown in figure 1.9, the solvent molecule will flow through the membrane from pure solvent to solution. This process of flow of the solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side to solution side across a semi-permeable membrane can be stopped if some extra pressure is applied on the solution. And this pressure that just stop the flow of solvent is called osmotic pressure of the solution. Solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. The important point to be kept in mind is that solvent molecule always flow from lower concentration to higher concentration of solution. The osmotic pressure has been found to be dependent on the concentration of the solution. The osmotic pressure of a solution is excess pressure that must be applied to solution to prevent osmosis, that is to stop the passage of the solvent molecule through a semi-permeable membrane into the solution. And this is illustrated in figure 1.10. Osmotic pressure is a colligative property that it depends on the number of the solute molecule and not on their identity of dilute solution. It has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature T. Thus, pi is equals to CRT. Here, pi is the osmotic pressure and R is the gas constant. Pi is equals to N by 2 by V RT, where V is the volume of solution in liter containing N2 moles of solute. If W2 grams of solute of molar mass M2 is present in the solution, then N2 is equals to W2 by M2, and we can write pi V is equal to W2 into R into T by M2, or M2 is equal to W2 into R into T by pi into V. Thus, knowing the quantity W2, T, pi, and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar mass of solute. This method is widely used determining molar mass of protein, polymers, and other solutes. The osmotic pressure method has the advantage over other method as pressure measured is around the room temperature and the molarity of solution is used instead of molality. As compared to other colligative properties, its magnitude is large even for very dilute solution. The technique for osmotic pressure for determination of molar mass of solute is particularly used for biomolecule as they are generally not stable at high temperature and polymer have poor solubility. Two solutions have same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by semi-permeable membrane, no osmosis occurs between them. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9 mass by volume solid sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cell in solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cell and they will such a solution is called hypertonic solution. If the salt concentration is less than 0.9 mass by volume, the solution is said to be hypotonic. In the case, water will flow into the cell if placed into the solution and they will swell. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water by osmosis and shrivels into pickles. Wilted flowers revive their place in fresh water. A carrot that has become limp because of water loss into the atmosphere can be placed into the water, making it forms once again. Water will move into cells through osmosis when placed in water containing less than 0.9% mass by volume salt. Blood cells swell due to flow of water in them by osmosis. People take a lot of salt and salty foods experience water retention in tissue cells and intramolecular space because of osmosis. The resulting puffiness or swelling is called edema. Water movement from the soil into the plant root and subsequently in upper portion of the plant is partially due to osmosis. The preservation of meat by salting and of root is by adding sugar protection against bacterial action, though the process of osmosis of bacterium on salted meat or candied fruit loses water, shrivels and die. Reverse osmosis and water purification. The direction of osmosis can be reversed if pressure larger than osmotic pressure is applied to the solution side. That is now, the pure solvent flow out of the solution through the semi-permeable membrane, and this membrane is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater. A schematic for the process is shown in figure 1.11. When pressure more than the osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membrane are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurity and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements. Abnormal molar mass. We know that ionic compounds, when dissolved in water, dissociate into cations and anions. For example, if we dissolve 1 mole of KCl 74.5 grams in water, we expect 1 mole of each K and Cl negative ions to be released in the solution. If this happened, there would be 2 moles of particles in the solution. If we ignore intermolecular attraction, 1 mole of KCl or 1 kg of water would be expected to increase the boiling point 2 into 0.52 K is equals to 1.05 K. Now, if we do not know about the degree of dissociation, we could be lead to conclude that the mass of 2 moles of particles is 74.5 grams and the mole mass of 1 mole of KCl would be 37.25 grams. This brings into the light the rule that when there is a dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecule of ethanoic acetic acid demerize in benzene due to the hydrogen bonding. This normally happens in solvent of low dielectric constant. In this case, the number of particles is reduced due to demerization. Association of molecule is depicted as follows. If it can be doubtably stated that if all the molecule of ethanoic acid associated in benzene, then TB or TF for ethanoic acid will be half of the normal value. The molar mass calculated on the basis of TB or TF will therefore be the twice expected value. Such a molar mass that is either low or higher than the expected or normal value is called as abnormal molar mass. In 1880, Van Sop introduced the factor I known as the Van Sop factor to account for the external dissociation or association. This factor I is defined as I is equals to normal molar mass upon abnormal molar mass. Observe colligative property upon calculated colligative property. I is equal to total number of mole of particles after upon dissociation. Association upon dissociation. Number of moles of particles before association upon dissociation. Here, abnormal molar mass is the experimentally determined molar mass and calculative colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of I is less than unity, while for dissociation is greater than unity. For example, the value of I for an aqueous solution of KCl is close to 2, while the value of ethanoic acid in benzene is nearly 0.5. Inclusion of Van Hoff factor modified the equation for colligative properties as follows. Relatively lowering of vapor pressure of solvent P1 naught minus P1 upon P1 naught is equal to I dot N2 by N1. Elevation of boiling point TB is equal to I into kV into M. Depression of freezing point TF is equal to I into KF into M. Osmotic pressure of solution phi is equal to I into N2 into R into T by V. Table 1.4 depicted value of the factor. I for several strong electrolytes. For KCl, NaCl and MgSO4, I value approach 2 as the solution becomes very dilute. As expected, the value of I gets closest to 3 for K2SO4. Now last part of the chapter, that is summary. A solution is a solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gas solution. The concentration of solution is expressed in terms of mole fraction, molarity, and in percentage. The dissolution of gas and liquid is governed by Henry's law, according to which at a given temperature, the solubility of gas in liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the presence of non-volatile solute in the solution, and this lowering of vapor pressure of solvent is governed by Raoult's law, according to which the relative lowering of vapor pressure of the solvent over the solution is equal to the molar fraction of non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solution are volatile, then another form of Raoult's law is used. Mathematically, this forms of Raoult's law is stated as P total is equal to P1 naught into X1 plus P2 naught into X2. Solution which obey Raoult's law over the entire range of concentration are called ideal solution. Two types of deviation from Raoult's law called positive and negative deviations are observed. A zero trough arises due to very large deviation from Raoult's law. The properties of solution which depends on the number of the solute particles and independent of their chemical identity are called colligative properties. And these are lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. The presence of osmotic can be reversed if a pressure higher than the osmotic pressure is applied to the solution. Colligative properties has been used to determine the molar mass of solute. Solute which dissociate into solution exhibit molar mass lower than the actual molar mass, and those which associate slower higher molar mass than their actual value. Quantitatively, the extent to which a solute is dissociated or associated can be expressed by Van Hoff factor I. This factor has been identified as the ratio of normal molar mass to experimentally determined molar mass, or as a ratio of observed colligative property to the calculated colligative property. अगर आप इस चैप्टर से रिलेटेड कोई भी सुझाव देना चाहते हैं तो आप कमेंट सेक्शन में जाकर के हमें बता सकते हैं। आपके सारे कमेंट्स हमारे लिए बहुत ज़्यादा वैल्यूएबल हैं और हम अपनी वीडियो को कैसे अच्छी तरीके से इंप्रूव कर सकें, प्लीज़ लेट मी नो। थैंक यू फॉर वॉचिंग दिस वीडियो, एंड इफ यू लाइक दिस वीडियो प्लीज़ डू शेयर, सब्सक्राइब विद माई चैनल एंड शेयर विद योर फ्रेंड्स एंड फैमिली। थैंक यू सो मच।